Okay, so here we'll do another example of this. We'll let D equal the event random person, randomly tested person has a disease, a particular disease like coronavirus, okay? Randomly tested person has disease. Is that clear? Whether they have it or not. Has nothing to do with the test, just whether they have it or not. It's not saying randomly tested person tests positive for disease. Randomly tested person has the disease. We'll let plus equal the event that a test, randomly tested person tests positive for E. Okay, there we go for the disease. All right. So the question is, find PD given plus. So find the probability they actually have the disease if the test comes back positive. And we're going to use these probabilities. You can think of these as coming from a model. You have to have something to work with. So we're going to assume the whole population, 5% of the population has this disease. This could actually be considered an underestimate in some places for coronavirus, or maybe not. But we're not interested in that. We're interested in our probability. So we're going to assume probability of the disease and just the general population. If you just take all, million people in Worcester County, we're going to assume that 1 out of 20 have the disease. We're going to assume that the tests operate as follows, that the probability of getting a positive test on someone with the disease is 99 out of 100. That means a false negative is 1 out of 100. We're going to assume the probability of a negative test on somebody that doesn't have the disease is 95 out of 100. That's good. That means the probability of a false positive is 5 out of 100. And there we go. And then we want to find the probability that if they have that if the test comes back positive, they actually have the disease. In some sense, you can think of the D as unknowable, right? All we get are either plus or plus complement, negative, and we are trying to infer whether they have the disease or not. Whether they actually have the disease, maybe it is knowable, but you need more tests, so we just don't really know. We could get a positive test and they don't have the disease. So we just do this using our conditional probabilities. So P, what is it? PD given plus. How do I do this? PD given plus is equal to, just use the definition at first to start if you're not sure. So it's PD plus over P plus. Well, PD plus, there's only one way for that to happen. There's two phases to this. There's the disease and the test. So this means they have the disease and they get the positive test. Okay? So, and this means the positive test. This can happen two ways, with the disease or without the disease. So we've got to now expand this. So this is equal to PD plus PD plus plus P, maybe they don't have the disease and got them, D complement plus. And now to compute these, because they're intersections, then it's not clear what these are, we will use the conditional probability. So this is P plus, given D, PD, P plus, given D, PD, plus P plus, given DC, PDC. which equals, these are all now direct from the problem. Probability of a positive test given the disease we said was 99 out of 100. So we have 99 out of 100. Probability of having the disease was 1 in 20. Let me leave some room here. 99 out of 100. 1 in 20. Plus the other way. What's the probability of a plus given you don't have the disease? Well, if you don't have the disease, 95 times out of 100 you get a negative test, which is good. But we're saying it's a 5% false positive, so 5 out of 100 times you do get a test. I'm going to write 5 out of 100, and I'm tempted to write 1 out of 20, but 5 out of 100. And then the probability you don't have the disease, that's 19 out of 20, just from the model. Okay, well, it's clear I want to multiply top and bottom by 2,000, and I will get equals, if I multiply the top and bottom by 2,000, I get 99 over 99 plus 95. Wow. Which is equal to 99 over 194. Okay, so it's only a little more than a half. So this is one of the perils of random testing, is that this is all due, so it's like the insurance company problem. It's due to the fact that most people in the population don't have the disease, right? It's this term. This term is, sorry. Why is this 5? Yeah, sorry, it's this term, the 19 out of 100 is pretty big. Most people don't have it. So even though the false positive rate is low, or maybe you don't think that's that low, this though brings it up. Okay, so the random testing is good when more people have it, and then this term will go down. But right now, 95% of people don't have it. So that amplifies the false positives and makes the fraction of the true positives smaller, as you can see. You can see the fraction right here. The true positives are slightly bigger than the false positives, but because the population, most of the population doesn't have it, the false positives is almost the same size. So this is actually, I understand, I'm not a medical person, but this is something with prostate screenings. This was a problem for a while because they would do regular prostate screenings at a certain age, and there was the test had a high false positive rate, and it would alarm a lot of people, and then they'd have to do more tests, and a lot of the secondary tests came back negative. I don't know if this is true for our current situation, but anyway, this is how you do it. So this was just the last example I wanted to do right now of using conditioning. Okay, so all this really shows you is the conditioning. We just took here, right here, we wrote this as plus. We wanted to write the event plus as the union of plus with the disease, a true positive, and that union of a true positive with a false positive to get that. So that was this down here. All right, moving on.